And there's no really airflow tool that I know of that tells you what a new install in location of the previous install is going to perform like. And that's what we've added to the tool that works with the app. The app now has a new functionality that's called forecasting.
Okay.
And what it does is everything I described earlier, where you pressure map the system and you get the raw flow, we correct it. We take that bucketed data and then we put it to work, which means like a designer would on a new install, you get your heat load calculation, you do your manual S, you figure out how much flow for the capacity you're moving, and then you do a duct design.
All right, everyone. Thank you for joining us once again on Did You Know, the ESCO HVAC podcast. So today we're going to be spending some time with our good friends over at the Energy Conservatory. How are you guys doing?
Good.
Hey, Clifton, how are you?
I'm doing great. We're going to spend a little bit of time talking about the importance of airflow and proper airflow measurement, especially as we move into a new generation of high-performance systems. We have the U.S. Department of Energy that is really encouraging the industry to re-look at its capabilities. We've got things like the cold climate heat pump challenge that is pushing manufacturers to come up with new designs and new capabilities of equipment to be able to produce excessive amounts of heat at low ambient temperatures. But in doing that, remember, we're still just talking about moving heat, right? We're all in the business of moving heat. And being able to move heat requires the most important factor, the ability to actually move heat in airflow. Now, in the past, we've had ways for, I always call it estimating airflow, right? Even if we're doing broad calculations, there are so many placeholder numbers in there that are not actual calculations. They're just like generally accepted numbers for doing calculations for temperature rises on, electric air handlers with heat strips, or using, fan tables out of installation manuals and not even really calculating exact voltage. And there's so many variables when it comes to using that airflow, but it really is like the most important thing of our job. Now, you spend a lot of time focusing on the entire shell of a home, but when it comes down to airflow, you've introduced something in the last, where are we at, about a year and a half now on the TrueFlow Grid?
A couple of years, yeah.
2 years. And a lot of people aren't aware of what we're actually doing. And in my opinion, and this is my own personal opinion, I'm sure it probably is of you guys as well, that really it's the only way to accurately measure airflow in a residential split system. And not only that, it gives us the opportunity to start using that data for things like forecasting, right? Understanding what we could do with new systems. Let's talk a little bit about, we all know the importance of airflow, but let's talk a little bit about the science of measuring airflow and why the TrueFlow Grid is actually so accurate.
I want to pass this question to Steve and have him comment because he did a lot of research on this. When you were saying accurately measure airflow, is there other methods? Yeah. So what I'd like to hear, I think what would be important to the audience to hear from Steve, and Steve, the story I think I'd like to hear you tell is one I've heard before, which is where when you did temperature measurements on your house and how long it took for the stability of that measurement to become stable enough to where you could trust it.
Ooh.
That's interesting. And I think it's worth people hearing because I've heard a lot of people, on like a furnace, they'll say, well, I'll do the delta on the furnace. And that's not to say it's not an accurate method, but how long does it truly take to get stability to where you can trust that?
Very good point.
Yeah. So I data logged the temperature in a supply register and watched how long does it take to get down to temperature. And my system really kind of never did. There was, if it ran for 2 hours, the supply temperature was going to be colder than it was even after 1 hour. And it's partly what was going on is there's some duct leakage in my trunks in the basement, and it just kept getting colder and colder and colder the longer it ran. But even if we're looking for a delta T, and what was happening there is that both the supply was getting colder and the returns getting colder. And so, but you did reach a stable delta T, but that really took more than 10 minutes, closer to 20. And the other thing is thinking about where you measure those temperatures. The one in the return is fairly easy. Normally it's well mixed. It's all the same temperature. But we're taught that you want to measure the supply temperature in the register that's closest to the air handler. And in my house, there's two different ones that are almost exactly the same distance, depending on whether I go off the northbound or the southbound branch of my trunk. And guess what? They're not the same temperature. They're like 2.5 degrees difference. So which one's the right one?
Exactly.
2 degrees difference in your 2.5 degrees difference in your delta T. That's pretty significant in terms of what calculation is for airflow. Yeah.
You betcha.
So on the other side of that, once Steve told me about that in the winter, I said, well, I wonder how that duct system plays out in Louisiana. So I did like my own case study after that.
Sure.
House that I knew it was a family home. So I was able to kind of like, do whatever I wanted to do. So I did a duct leakage test on this job, and the duct leakage was very, very small. We're talking about like 27 CFM. And we did some work to get it tight just because I didn't want duct leakage to play be a factor, to be the big factor in that.
Yeah.
And I was getting from the closest grill to the furthest grill about 4 degrees of separation. At this point, the attic was about 130 degrees.
Sure.
Right. So it's like little factors like that. So it can be accurate, but there's things you got to know and pay attention to if you're using, say, that method. If the system gets dirty, then TESP kind of falls to the wayside. So everything has got some level of an Achilles heel to it, I guess is what we're trying to say.
A lot of professors, if they're really into airflow teaching in the trade schools, might teach pitot tubes, and they're used all over the place in commercial. But anybody who's ever tried to use a pitot traverse in residential knows that it won't work. There's just never enough straight duct like you would have in commercial. And, you're not going to get, it's a random number generator.
Sure.
So
when you think about all the additional turbulence that you have inside duct work, and, you can place even in just one supply, you can move around in different areas of one supply and have a variety of different measurements depending on turbulence and how much heat transfer, how much the air is slowed down in certain bins and places of bins. There's a lot of variables that go in there. So traditionally, we're using calculations with approximate numbers to get a approximate airflow as close as we possibly can. Mm-hmm. We know in reality, when we're doing performance and measurement and performance analysis and actually determining the actual BTU transfer that we have over a heat exchanger, that airflow becomes an incredibly important calculation. And so as we start looking at technology and utilizing technology to get more advanced measurements, it was inevitable that eventually we would start looking at airflow as one of those components. We already use highly accurate temperature thermistors and highly accurate pressure transducers to be able to come up with numbers that we can calculate very efficient, calculations, outputs. And so that, I'm sure, was kind of like the evolution of where the TrueFlow Grid came into design. And all right, let's use technology to get as accurate as we possibly can.
Yeah. And actually, so there's many people don't know this, but the TrueFlow is actually generation 2, the one that people are learning about a lot today. Generation 1 was made more than 20 years ago as a result of some DOE funding. Where they wanted to try and figure out what's a good way to measure airflow in residential systems.
Really?
So the Energy Conservatory 25 years ago-ish worked with some DOE funding and some other researchers and developed the original TrueFlow, which, some people know it if they've been in the industry a long time. It was a transparent plastic with holes in it, similar to what we have today, but then it had this, copper tubing array on the back. And it was accurate and, reliable, just like the one we have today, but not connected. You had to snake the pressure tubes out of the door in the filter slot and connect them to your DG1000. And, we'd get you a flow, but didn't help guide you on if that's a good flow or not a good flow.
What does it mean?
What does it mean? And if it's too low, well, where's the restriction? So that was the point of Gen 2. We wanted to make it easier, and we actually made it significantly cheaper too. It used to be, quite expensive, and guide the users with the app on what does that number mean and what do I need to do to the system to get that airflow where I want it.
Wow. So tell me about the use of the TrueFlow and what I'm actually going to be doing and what it can show me in this version 2 model that we have.
Why don't you take that one, Chris?
Yep. So like Steve was saying, it's the TrueFlow version 2. It's Bluetooth. So it's a grid that takes differential pressure drop across the grid. It fits into an adapter plate. The adapter plate takes the place of the return. So we pressure map the system with an app. The app connects to these devices to give you the workflow. So the app guides you where you should take the pressure measurements. Once you get into the supply, your last pressure measurement, you're going to ask to take that pressure in what we call the NSOP, normal system operating pressure, or filter in pressure.
Yeah.
After you take that, you'll take the grid which in its adapter plate, you'll slide it out. You'll put the grid in that location. At that point, we're taking a raw flow measurement across the grid, also capturing that supply pressure again. And then we're taking those two supply pressure measurements, one with the grid in, one with the filter in, and the raw airflow measurement across the grid. Those 3 points of data allows us to calculate what the flow was when the filter was in location.
Yeah. You're getting a complete traverse calculation off from it. Wow. Okay. So by doing that, we can actually, if I'm looking at this from a technician perspective and I'm looking at a system retrofit, say I'm doing a high efficiency upgrade, right? I'm going to be going from maybe a traditional fossil fuel or maybe from a lower efficiency heat pump, and I'm going to be looking at a high efficiency heat pump installation. I actually want to be able to take these calculations before I even remove my equipment.
Yeah, so this is a fun talk. This is a new feature that here's what I'll say.
Okay.
When the tool came out, there's a cost to everything. And so a lot of people, I think, looked at our tool and said, hey, that's really cool, but I get airflow that way, and I get airflow this way. And so a differentiator that is new is what we call forecasting. And there's no really airflow tool that I know of that tells you what a new install in location of the previous install is going to perform like. And that's what we've added to the tool that works with the app. The app now has a new functionality that's called forecasting.
Okay.
And what it does is everything I described earlier, where you pressure map the system and you get the raw flow, we correct it. We take that bucketed data and then we put it to work, which means like a designer would on a new install, you get your heat load calculation, you do your manual S, you figure out how much flow for the capacity you're moving, and then you do a duct design. Well, in a retrofit application, all of that is installed already, right? So you're not typically doing a design from scratch.
Yeah.
You should be doing a load calculation, right? That way you know how much capacity you need to put back in, because let's just face it, a lot of systems probably aren't sized right that are currently installed. So we do a load calculation. Then you select a piece of equipment you want to use to put back. But then the question is, in that expanded performance data for that piece of equipment, how much airflow does it need to move?
Yeah.
Well, if you can go do that minor research and get that data point, and then you give that to us in the forecasting, we will then tell you how what's already installed, the ductwork, the current filter, we're going to tell you how that responds based on that new piece of equipment's airflow. That way, it's like you're not playing the guessing game of like, well, the existing system's doing okay on this duct system. Is the next system going to be working okay? And I think the biggest question that people are having right now with the heat pump movement that's alive is heat pumps are moving roughly 400, CFM per ton, switching over to heat mode. Yeah. Furnaces aren't moving that, relatively speaking. I mean, some are moving quite a bit of airflow now with a lower delta, but historically that's not the case. And if it was designed properly and heating was the dominant flow because it was such a high heating load, well, that ductwork's probably not going to be sized appropriately for the heat pump that's going to take its place. And so currently right now, you could know that. And we just need to know the flow from the heat pump you want to choose. And we'll be able to give you the green light or the red light for moving forward.
That is absolutely crucial when we start talking about inverter systems. Most people don't understand the true calculation that an inverter does for capacity, right? When we look at traditional, say I've got a PSC driven or an ECM constant torque driven, whether it's an air handler or a gas appliance, external static pressure always has an effect on our motor. It always has an effect on the capability of the motor and the airflow that we can move. When we start moving into fully modulating systems that are using variable speed blowers, especially when we start talking about inverters that are using electronic expansion valves, that external static pressure becomes an incredibly important factor for capacity. Because previously, if we were talking about a system, external static pressure may reduce our airflow, but it didn't affect the actual capacity drive of either a modulating gas furnace or our single or two-stage outdoor unit. When we get into inverter systems, external static pressure actually goes hand in hand with capacity, because as we start reducing the ability to move heat through our airflow because we have that excess restriction, our system is going to respond because we're measuring, we're calculating by superheat and compressor discharge temperature. And that inverter is actually going to modulate down once it starts getting that excessive airflow. And I can tell you, as a technical support specialist for one of our major manufacturers, that was the biggest issue I had with contractors when they were taking out traditional systems and they were putting in modulating inverters, is that they weren't getting capacity out of it. And I do site visits, go, oh, by the way, you're operating at 60% because you got a 1.1 external static pressure on high fan speed. And they go, well, I don't understand that. I wish I would have known that beforehand. Now you can.
Yeah.
So I will say one thing that I think the manufacturers of equipment are starting to pick up on, and we're happy they are, is it's a very sticky situation between technicians and manufacturers of equipment. Manufacturers want to sell that equipment to the technicians. Technicians need equipment. But a manufacturer, it's not a good look for a manufacturer to go to their technician's job and say, well, you didn't do that right. Right? Nobody wants to see that. That's not a good conversation to have. And most reps aren't. It's a tough conversation. I've been there. Okay.
And you got a homeowner standing there going, hey, what's this conversation about?
Right. So, I mean, I hate to say we're like we're the source of truth, but it's nice. I think manufacturers are looking at our tool thinking, ooh, they can say it.
That's exactly right.
It's not us. It's they, and meaning TEC.
It's a third party.
It's a third party. It's just it's like, I'm looking for a good analogy here, but it's just the one I have on the top of my brain. I'm not going to say.
Not audio appropriate. Used to say TV appropriate. Now it's audio appropriate. Not airwave capable.
Let's just say there needed to be a middleman, and without a middleman, nothing was getting fixed. Right? It just became a whole bunch of talk, going back and forth, and a whole bunch of pride. And what I feel like we've done is we've become a mediator, right? We're the middleman that says, hey, we've got a source of truth there. Let's put it to work and let's just get down to brass tacks and, let's put an answer here.
Absolutely. Well, you think about how many systems we know are oversized. They were, especially our older homes. If I've got a home, more than 30 or 40 years old, it was probably never designed for the airflow of air conditioning, let alone airflow of heat pump. And so we just continually upgraded capacities. One contractor would take out a 2-ton and go, that wasn't big enough. Let me go ahead and put this 2.5 in for you. Next contractor comes by and takes the 2.5 and puts a 3-ton in. And the next thing we know, we've got a 2-ton of ductwork with a 3-ton system. We've lost 5 compressors over the last 10 years. And so we're just going to put a new system in it again without knowing where we're at.
And to your earlier point, none of those systems was ever putting out much more than 2 tons anyway because it couldn't move the air.
Exactly.
So one thing I'd like to say, Clifton, is this. Not everybody needs to run out today and go buy a TrueFlow. Would we love that? Yeah, we absolutely would, of course. Who doesn't want that to happen when you're in the business of making sales? But it's not that we left everybody hanging. Like if you've looked at the development of our app, we've took strides to bring people along. What I mean by that is like right now, if someone just has any manometer that they have, right? And you can get a manometer relatively pretty inexpensively. It may not be a micro manometer, but it's a manometer nonetheless that you could use with a fan curve chart. You could pick one up. What I have learned is a big struggle, nationally, is there is a lot of people who are saying, man, I don't know where to take those pressure measurements yet, right? They're going to training to learn where to put the probe.
Right.
If that's where we're at, we decided we need to meet you there, right? And so let's start there. And if you live there for a while, there's nothing wrong with that. And that's free. Right. So what we're trying to do is say, hey, if you go to a training, there's a lot of theory talk and then there's a lot of practicality talk about how to do it. It's a lot. There's all these studies about how much you actually retain from a classroom training, right? Maybe 15% over the long haul. But if we can organize the data, that way that's less you have to remember in the class. You can just follow the procedures. We wanted to do that. So like you can use the logic at no expense at this point. And I think we're pretty happy about that. That kind of falls in line with who we are as a company,
Right.
you know?
Yeah, so let me just restate that you can use our app without any TEC equipment. So just our app for free using any manometer. And then the pictures in the app will guide you on where to take the static pressure measurements and then tell you what your total external static is, and also break down how much of that is supply, return, filter drop, and evaporator drop. And then you can use that TESP in the manufacturer's fan chart, having certainty that you measured in the right place. And then manufacturer's fan chart will be more useful. So that's Chris is talking about. We want to make that on-ramp easy because we need to move beyond airflow is good. You know, we've all heard this. Airflow is good. Airflow is not good. Airflow is measured.
Right.
If you don't have a measurement, then you don't know. Yeah. Airflow is good too often means airflow is probably bad. And so helping technicians on that path to here's where you make the measurements. Here's what the TESP is. You don't have to break out your calculator and do any calculations at all. And then that's the number you can use right in the manufacturer's span charts. You know, as we talked about, that works great for commissioning new systems in that like new condition. The manufacturer span charts are usually pretty good. But if you're trying to replace a 20-year-old system, that might not even have the original motor in it.
Right.
The evaporator coil is probably dirty. The blower wheel is probably dirty. It's not going to match the manufacturer span chart anymore, very likely.
I just want to add to that. We're not replacing training. We're organizing data, but we're not replacing training. There's still things you need to know. Where in that supply plenum is the best spot to take TESP? Where on the return side should you take it? Just a mildly quick example here. If you have a vertically installed furnace and there's a filter slot next to it, if you take it right after the filter, but maybe not in the cabinet, did they cut the hole out all the way on that furnace? Or did they leave just a 10-inch hole? You're not going to know that if you pressure map in the wrong spot. There's things that no technology is just going to do for you that you need to hear it out of somebody's mouth in a real training and learn it, right? So training's still needed. And I would encourage that, but that's what I mean by let the app collect some data for you. That way you don't have to remember all of that.
And I'll make a quick little plug for those, who are thinking about equipment and how are they going to train on airflow. We'd love to figure out how to get more TrueFlow kits in the hands of educators in their programs. Lots of you may have been just teaching with manometers and pitot tubes, which of course in residential is not a good way to go. It's not going to get you good results. So reach out to us, reach out to Chris Hughes. We do have an educator's discount on that equipment, and hopefully your program can get into that and you can teach technicians that, it doesn't have to be black magic. There are tools available now that can make it easier to figure out, is the airflow correct? And if it's not, what's wrong?
Absolutely. So if I'm an educator and I'm looking to connect, if I am a contractor and I'm looking for better resources to use my existing dual port manometer, or I'm a contractor and I'm looking to upgrade into a TrueFlow Grid, what is the best way to connect?
Well, I think you got to ask yourself, what type of learner are you? If you're ready to make a purchase, you could go straight to a website. If, like Steve said, if you're an educator, we have an educator's discount. I would say get in touch with me through email. I'm pretty easy to find. If you are wanting to just learn more about how it all works, our YouTube channel is pretty good for that. I've made quite a list of videos. There's pretty much a brand new forecasting video that's out that's pretty thorough. That's performed on a real job, not just kind of like in a lab.
Right.
I thought that was kind of fun. That's kind of the avenues I would take.
Okay, fantastic. Well, everyone check out the Energy Conservatory. And if you want to join us and spend some time hanging out with the crew, we'll see you at the National HVACR Education Conference. Everyone have a wonderful day. Thank you, gentlemen.
Thanks, Clifton.
Thanks for having us, Clifton.